In this video, we're going to implement the bubble sort algorithm that we just went through using slides in the last video. So I'm going to start by creating a new project. Now I'm going to go through this one more time. And then from this point forward, I'm going to assume that you understand how to create a project. So when we start a video, I'll already have the project created. But for one last time, we go up to File, New, Project. And I want a Java project, so I'll make sure Java is selected on the left-hand side, and we don't need to check any of these boxes. I have my project SDK set to Java 9. I'm going to click Next. I want the IDE to create the main method for me, the main class and the main method, so I'll select that and click Next. And I'm going to call this project Bubble Sort. And I'm going to change the package to academy.learnprogramming.bubblesort. And I'm going to click Finish. And because I have a project open, it's asking me if I want to use the same window, and I do. So I'm going to click this window. And there we go. We have our new project. So I'm going to move this over a little to make some more room. I'm going to delete this comment. And this is a rather simple algorithm, so we're just going to do the implementation within the main method. Now, before we do that, I'm going to write a swap method. As you'll see, a number of the sort algorithms will look at swap elements at some point, and that's true of bubble sort. It swaps elements, so I'm going to write a swap method. So I'm going to say public static. It has to be static because we're going to be calling it from the main method, void swap. And this method's going to take three parameters. It's going to take the array that we're sorting, and it's going to take two indices. And these two indices are the indices of the elements we want to swap. So if we wanted to swap elements 3 and 4, we'd pass the array in, and we pass 3 for I and 4 for j. So the first thing we're going to do in this method is check whether I equals j. Because if I equals j, there's nothing for us to do. So I'll say if I equals j, we'll just return. Because essentially if I equals j, we're saying we want to swap, element 2 with element 2, or swap element 3 with element 3, so there's nothing for us to do. There's actually no element to swap. But if I isn't equal to j, then we do have elements to swap. And so what we're going to do is we're going to create a temporary int variable, and we're going to save array I into that variable. So temp will now contain the value at array I. And then we're going to assign the value at array j to array I equals array j. Now it's okay for us to do this. We've overwritten the value that was at array I, but that's fine because we've saved it in temp. And so the final thing we have to do is assign temp to array j. So we'll say array j equals temp. So we assign what's at I to temp, we assign what's at j to I, and then we assign what's at temp to j. So when we exit this method, what used to be at position j will now be at position I, and what used to be at position I will now be at position j. All right, so now that we have a swap method, let's create our int array. So I'll say int array equals, and we'll use the same values we used on the slide, 20, 35, minus 15, 7, 55, 1, and minus 22. And now we want to use the bubble sort algorithm to sort this array. Now, the implementation that I'm going to show you is one implementation. There are other implementations of this algorithm. There'll be a different implementation to sort in descending order. Some of the implementations expand the sorted partition from left to right rather than from right to left. I'm going to implement what I showed you in the slides. And so we're going to say for int last unsorted index equals array.length minus 1. That should be int array actually. So remember that at the beginning of the algorithm, the entire array is unsorted, and so the last unsorted index will be the last valid index in the array, and that's int array.length minus 1. So that's what we're initializing that to. And then we're going to do this as long as the last unsorted index is greater than 0, and after each iteration, we're going to decrement the last unsorted index. Now remember that because we're bubbling large values to the end of the array, the sorted partition is growing from right to left. And so the last unsorted index starts at 6, and after the first iteration, it's then going to be 5 because whatever's here will be in the sorted partition. And then after the second iteration, it'll be 4 because then these two elements will be sorted, and then 3, 2, etc. And so the index is going to go from 6 to 0. And once we hit 0, we can stop because at that point, the entire array is sorted. So that's the outer loop. For each iteration of the outer loop, we want to traverse the array and we want to bubble the largest value that's unsorted into the sorted partition. So we want to bubble the largest value to the end of the array. So that's what the inner loop is going to do. So we'll say for int I equals 0, because we always start at the beginning of the array. I less than the last unsorted index, because we don't need to go into the sorted partition because we know that the values in the sorted partition are already sorted. So in the inner loop, we start at 0 and we keep going until we hit the last unsorted index. And we're going to increment I. And then what we want to do, as you saw in the slides, is we want to compare the value at I with the value at I plus 1. And if the value at I is greater than the value at I plus 1, we want to swap the two values because we want to bubble the largest values up to the end of the array. And so we're going to say if int array I is greater than int array I plus 1, well, what do we want to do? We want to swap them, and we can use our swap method to do that. So we'll pass it the int array I and I plus 1. And that's it. That's our implementation of the bubble sort algorithm. As I said, this is not the only implementation. It is a implementation, or should that be an implementation? So we're sorting in ascending order, and we're bubbling large values to the end of the array, and we are growing the sorted partition from right to left. We're starting it right at the end of the array, and after each iteration of the outer loop, the sorted partition grows by 1. And so it starts out being basically nothing in the sorted partition, and then after the first iteration, the element at position 6 is sorted. So that's the sorted partition. After 2 iterations, the elements at positions 5 and 6 are sorted. So that's the sorted partition, etc., until we get right down to the beginning of the array. So let's print out this array after we've sorted it. So for int I equals 0, I less than int array dot length I plus plus, and we'll just print out the value in the arrays. So int array I. So this should work. And when we run, these values should be sorted. Let's give it a shot. And sure enough, our values are sorted. Minus 22, minus 15, 1, 7, 20, 35, and 55. I'll just close the console here. And so that's bubble sort. Now, I said in the last video that the time complexity of bubble sort is O to the n squared. It's quadratic. So the absolute worst case is it will take n squared steps, where n is the number of items we're sorting. Now you might look at the code and say, well, it's not n squared. It's actually less than that because the sorted partition is growing after each iteration of the outer loop, and the inner loop doesn't cross into the sorted partition. So the inner loop is actually doing less work as the algorithm progresses, or at least as this implementation progresses, and you'd be right. But remember that when it comes to determining the time complexity of an algorithm, we're not doing math. We don't want the absolute precise expression. What we're trying to do is get some sense of how the number of steps grows as the number of items we have to sort grows. So we kind of want a general idea. We want to be able to say, this is a linear algorithm, or this is a quadratic algorithm, or this is a logarithmic algorithm, or this is a constant algorithm. It doesn't grow as the number of items you're dealing with grows. And so we're looking for approximations. The algorithm grows in a quadratic way as the number of items increases. The pattern isn't linear, it's not logarithmic, and it's certainly not constant. And so we still consider bubble sort to be an O to the n squared algorithm. And in fact, this implementation has a little bit of an optimization. Strictly speaking, bubble sort wants us to traverse the entire array every single time. It doesn't really pay attention to where the sorted partition is. This implementation does pay attention to where the sorted partition is, and it doesn't cross into the sorted partition because it doesn't have to. Those elements are already sorted. One tip when it comes to determining time complexity is to look at how many loops there are, because normally each loop corresponds to n. And so if you have only one loop, then it's linear time complexity. If you have two loops, then it's n times n. And so that's quadratic time complexity. And here we have two loops. And so just at a glance, we can kind of guess that this is O to the n squared time complexity. All right, so that's bubble sort, not very complex. As I said up front in the theory video, this algorithm is one of the least efficient algorithms. In fact, there are some computer scientists that think we shouldn't even teach it anymore, but it is a classic sort algorithm that is usually taught, and it's gotten us warmed up for some of the faster algorithms that we'll look at later. So I'll see you in the next video.